Good afternoon, ladies and gentlemen. Sorry for the delay. I hope we'll make it up with the content. This is Jacky. I'm from ESD Acoustic, and I'm here to introduce some progress that my fellow colleagues and I have made these years. It's about horn and field coil technology, as you can see. And if time allows us, I'll also introduce a new structure applied in the electronics. So our research is based on Dr. Bruce Edgar, who is known for Edgar Horn, and Mr. Sam Say, who is a field coil driver expert. Great thanks to them. Okay, so first is our development of carbon fiber horns. This is what they look like. So these are two big subwoofer carbon fiber horns, and then the mid-range, and two little ones for the tweeter, and then two big ones for the bass. This is also the world's first set of carbon fiber four-horn system. At present, people are making wood horn speakers out of wood, metal, or plastics, sometimes glass fiber. So wood has been popular and highly regarded because of its fiber structure. We know that the horns, the last thing we want for horn is to have resonance and the penetration of sound, because that way the horn structure will not work. So wood has its advantage of being a fiber material because it has multiple layers. So with multiple layers of uneven material, then the sound will be harder to penetrate because at every layer it will be reflected some. So basically, and glass fiber on the other hand is like a little bit upgrade version of wood. It's 1/10 the diameter of wood fiber. So in this sense, carbon fiber is even better because it's 1/50 the thickness of wood. So in this way, we can make the horn much thinner, but with better capability. Furthermore, our carbon fiber is very heat insensitive, so no matter it's winter or summer, it remains exactly the same shape. We know that the horn curvature is very important. We want it to be always the same, so we keep the most natural and least distorted expansion. Okay, and the other thing good about a carbon fiber is it's very stiff and light. So it gives us more options in our design. As you can see, this subwoofer here, it's reaching up to the ceiling instead of to the ground. So this kind of structure cannot, it's like a mission impossible if we use wood for the material. Only carbon fiber can do this to keep it comparatively light. I have to explain that this is not purely carbon fiber. Despite its super characters, we still don't want a single material for making the horn, because a single material only has one resonance character. So this is if we have more materials, then it's harder to resonate. So depends on the cutoff frequency of our horns, their working range. We have different thickness and different material in it. This is a brief illustration of the sandwich structure. It's very easy to understand. So. We also, aside from this, I guess you guys know that boats have the keels to strengthen their structure. So our horns, since we have a middle layer, we also put some keels. It's odd number because odd numbers are better against resonance. So there's it's like a bone, like bones of body, yeah. So we have odd numbers of bones inside our horns, so the structure is even stronger. Yeah. So the other thing is if a horn does not have enough damping at its mouth, at its cutoff frequency, it will enter what we call the ring mode. like a ring, yeah. So therefore, we have made the mouth thicker, like this. Inside this ring is like a structure of soft material, much like sand. Because sand is very hard to resonate, the resonance inner consume each other, all the little sand. So based on the same principle, we put in this soft material to get rid of the resonance. So if the vibration tries to excite the horn into the ring mode, it's inner consumed. Now I would like to get a closer look at our bass horn design. This is a simplified specification of its structure. This is what it actually looked like. So this is a very unique design. As I have mentioned, it's reaching up to the ceiling instead of the ground. And it's also it's a straight and a round horn. Usually for sub bass, people have developed a folded horn for this application. So this is a first try, and we know about the corner horn design like a louder horn and clips horn. They utilize the ground and walls for what we call the near field effect to get a better bass out of it. So based on the same principles, we are using the near field effect here, but the difference is we are utilizing the ceiling. The advantage of this is first, we save a lot of space. So we can make a very large horn, but still does not take that much space. And the other thing is we are a five-way system, as you can see here. So our bass horn can still utilize the ground. And as you can see that the big horn has a turn in the middle. So what I would also like to show you our design here. This is a specification of the structure. Well, first thing first, a lot of people have the impression that big horns are good to be spiral, like a snail. It's like water flowing out of it, but I have to clarify that sound waves are waves. They act like light rather than water flow. So what we want is a mirror instead of a tube. So this way, I design a periscope-like reflection here. This reflection surface, I call it a turtle. It's very requiring because we want to reflect the lower frequencies. They are very penetrating. So aside from putting a lot of layers of carbon fiber, we also use different materials to based on the same concept of our sandwich design to let it be more reflective. Well, and also you can see that after this periscope reflect, no matter the sound comes from the middle, the side, they all carry on their own expansion curve. In this way, we are able to control the phase. Like if you have a spiral horn, the problem is that you don't actually know where the phase is. Although it's not that critical for bass horns, but actually I can tell you that you can hear the difference. Okay, that finishes our part of horn design. And now we are coming to the field coil. This is an explosion view of our field coil driver. It's actually simplified anyway. Field coil has always been renowned for its big magnetic power, but I know that not many people are doing it right now. There are several issues with field coil before us, like overheating, for example, and then disturbance from the power supply. So these problems have led the speaker industry to switch to field coil to permanent magnet. But time has changed because when field coil was mainstream, our electronics industry were not that advanced. We did not have control chips. But right now, the electronics industry has already developed to the point where controlling the circuit is not that hard, actually. So it's in this sense, this is not a return of an obsolete technology. We have done some major improvements. So first is, of course, we solved the problem of overheating by applying a heat sensor control chip inside. So it always sends the heat and controls it to protect it if it overheats. And the second thing is that in the old days, field coil drivers has been supplied by constant voltage power supply. The problem with this is that when the coil heat up, the resistance go up. And then with constant voltage, you have less current in this sense. However, magnetic flux is proportional to the current instead of voltage. So in this way, the magnetic flux gets down when the coil heat up. So instead, we have kept a constant current in the coil instead of constant voltage. In this way, the magnetic flux remains constant. The biggest breakthrough, though, I must indicate, is that we solved the problem of eddy current. Since the speaker industry was born, this problem has remained unsolved. So when this is in the gap and the voice coil is moving up and down, it's cutting the magnetic induction line. So it creates an eddy current that ultimately tries to stop the movement of voice coil. Many people have sought to solve this problem, but with permanent magnet, you can't really do anything because you don't have a circuit to control the flux. And now we have put a negative feedback circuit in the field coil power supply unit. So now it can balance out all the negative influence of eddy current. In this way, the diaphragm always moves as the signal tells it to do. It's always linear. Okay, now that we want bigger power here, because we use field coil, of course we want bigger power. So we would also need a driver structure that allows us to apply a bigger magnet. And also we have changed the material in our magnetic circuit to permalloy. Don't know if you know about that material. It's also called supermetal alloy, very expensive, close to silver, and it can provide 2.4 Tesla. And the usual magnet speaker can only reach about 1. Yeah, so this is like average number for speakers because this is out of laboratory. This is the highest Tesla you can get. You can use superconductor with close to 0 temperature, but that's not doable in a speaker. So now the structures, it's simplified. It's simplified. So we know about these two. These two are what we are having right now for our compression driver for the horns. And this one is front firing. This one is backfiring. There are problem with both of them. So as we can see here that the dome curve is like this. So when it exits the dome, it tries to expand. But with this face plug design, it twists the sound wave to go back. And then with this design, we can only have one slit if you are to have the path the same. So in this way, you got problem with the face in this front firing, and also there is distortion because you bend it with force, bend the sound. And the advantage though with this is that you have unlimited space for the magnet. No matter how many space you want for the magnet, you can. And the other one, backfiring, it's it's got a reasonable phase plug design. As you can see here, you can design the slits to be always perpendicular to the dome, so it's always in phase. But the problem with this is that if you want to couple it to a horn, you're going to have a flare rate. Then then the center pole is going to be thinner and thinner and thinner. So to a point, you can't do it anymore. Then our place for the magnet is limited. So this is okay if you don't want bigger magnet, but we are very ambitious. So we developed a different diaphragm. The common point with the front firing and the back firing design for drivers is that they use this kind of diaphragm. The voice coil is on the other side of the curve. So what we have developed is like this. In the advantage of this is that we can have a new design. So as you can see, it combines the advantages of front firing and back firing. With the curve, you can still have a very reasonable phase plug. So the phase is great, and the flare rate is reasonable, and you also have unlimited space for your magnet. Otherwise, we can't reach 2.4 Tesla, as I mentioned. Okay. Oh yes, our mid and high drivers use beryllium, but beryllium can the biggest beryllium diaphragm right now is only 4-inch. So this one has not been applied to our products yet, but we just developed them. This is a titanium sandwich diaphragm. It's titanium on both sides, and in the middle it's like a beehive shape. So it's very strong, yet remains very light. I can bend it with great force, but it's not going to damage. I can pass you around to have an experience yourself. You can try to bend it with hand. You're not going to damage it. Oh, and usual metal domes have the problem that they resonate, but with the sandwich one, yeah, it sounds kind of like a paper cone. The damping is really great. And also, by applying titanium, we keep the high velocity, high speed of sound inside the dome. So the center and the side, they produce the sound almost at the same time. That's some problem with paper because the speed of sound within paper is very slow. So there's a time delay problem. And I would also like to introduce a little bit about a new kind of structure applied in the electronics. This is what we have discovered after we researched it into horns about the resonance. Because I'm from China, by the way, so I don't know if you guys are familiar with Chinese architecture. There has been many wooden structures, but no screws at all. They can stand against earthquake for thousands of years because they are like super complicated building blocks, like this. So when they apart, they're kind of loose. And after everything is joined together, it suddenly becomes very nice against vibration because there are like very small gaps between each of them. So when the vibration comes in, they're like the same idea with sand. They are inner consumed. So we apply this to our electronics. In this way, it saves the trouble of getting extra frame, and also it's an outlook design. They are like furniture in this way. Yeah, that concludes my lecture here. So thank you very much. It's do you guys have questions? Yeah. Yes, we have the system on the show here, but I'm informed that we are not allowed to do propaganda here. So if you, okay, we are in hall 4, SO8, room SO8. Yeah, we are called ESD Acoustic. It's our first show, so the room is kind of small, but we can't hope for better. Yeah, for this system, the bigger the better. You can see it's like a tiger crowded in a cage. Yeah, we have active crossover, and it's 5 ways, and we have Class A amplifiers on both sides. And they are single-ended, so even if they are solid state, they sound much like tube amps, but they don't have that big background noises because horns are very sensitive. If you have high background noises, it's gonna be annoying. Yeah. And yeah, with 2.4 Tesla, we are able to reach, and horn, we are able to reach 120 dB for our mid-range chip.